Okay, the data sheet here, it generalizes the data that we need for our design. Okay, in normal practice, there is a data or information regarding thermal, mechanical ratings, limitation in terms of voltage, current range, and safe operating area tables, switching and on or off characteristic of the specific device. So all of this data is required for you all in terms of production, expectation or design. As we can see, in practice within the market, you have to take care of the design at the earlier stage, because the cost of change during design time compared to after the production stage, the cost is very huge. So that's why we need to rectify or estimate or design nicely, precisely, or at the best on our system. Because once we deliver or mass production to the market, the repair cost will be very high. Yeah. So prevention cost, if at the earlier stage, is quite high, but we try to reach the optimum level of total cost. That's the target or the practice in the market. Because once you deliver your product to the field, once your product fail at the field and you have to recall all the product and repair, so you will see that the total cost of your device or product that you deliver to the market will be defeated by the repair cost. And so this is the doom for your company. And so based on our syllabus or our outline subject for this thermal management, our scope here, we will refer to this 5 data sheet first, and if required, we will refer to the other data sheet that need to be looked at. So each of the data sheet we see here, it came from different kind of manufacturer, and you can see the data sheet number 4 and number 5. We are referring to same part number, but one of it from international amplifier and another one from Vishay semiconductor. So both retain same part number, but in detail we can see later on that the device came with different kind of characteristic. So if we take a look at the device itself, it came in multiple sheets of data or information, not only single sheet but maybe up to 10 of sheets. So each of the data, they have some sort of the front page information, general knowledge or general information regarding each of the device. So let's say if you refer to datasheet number 2, yeah, this is for the SCR or thyristor. So we have BTW67 and BTW69. So this is the front page of your device. It's stated over here that the device can cover or can operate up to 5 ampere of current operation in terms of RMS current up to 5 ampere. Meanwhile, it can hold or it can withstand voltage up to 1200 volt and gate terminal at 80 milliampere. So general description is given. This is a high power package, means that it can conduct high current, 50 ampere. It based on the chip. So in terms of mechanical appearance, we can see that the device BTW67 is different compared to BTW69. This is in terms of package which we have a horizontal placement to the heatsink. We have metal tab with the hole, so the purpose is to attach the heatsink to the device. This one is the through hole type, means that we have 3 legs here. The purpose of this leg is to insert to the board, PCB board. Meanwhile, the metal tab behind here is to be attached to the external heatsink. So it means that this device need heatsink to operate. You can operate without heatsink, but the capability of 50 ampere that is stated at the front page cannot be achieved. So if we look at the datasheet number 2, so it's stated over here that the device can go up to 12 ampere in terms of current operating, and it can hold or withstand up to 100 volt in terms of voltage. So if you put inside your circuit for rectifier, converter, whatsoever, so this is the rating that you have to take into account. So you cannot put into line voltage which is 230 volt operating voltage within which this kind of device. So it's stated over here the features of this device and typical application for usually being used for this kind of MOSFET. Used inside our width modulation control motor circuit or supply converters and whatsoever. So this is the front page. So what means that this is the dashboard of your device. Same with the dashboard of your cars. You can see here we have 2 kind of dashboard. Of a cars out there. We have a high performance car which can go up to 220 km per hour. We have a car which can go up to only 140 km per hour. So maybe this one is referring to this kind of car. Meanwhile, this one is referring to this kind of car. So in the first or at the first appearance, you can see that, or we assume that this car is better than this car, and for sure because we see at the dashboard. But in terms of application wise, let's say that we are going to move from one point to another point, and so let's say we are moving from Unimed to Kanga. We're going to use the same route. Doesn't matter you drive a high value or high end of car or this kind of car, so use the same route. We will face the same kind of traffic, same kind of jam, same kind of bumper, same kind of junction. So at the end, the average or overall in terms of distance is the same. In terms of the speed, also almost the same. You are not able to use the full force of 240 km per hour from Unimed out to Kanga because of traffic lights, junction, and all the obstacles that you face. Same goes to you if you use this kind of car. So overall, maybe the average distance or kilometer per hour that you are driving throughout the journey is around 60 to 80 kilometers per hour, even though you use this car or this kind of car. So it means that you have to design based on certain application and certain limitation. So from the car point of view, we can see that we have a dashboard which shows us the panel regarding our RPM, how much RPM we can push on, and how much the speed we can go up to. So both of these parameters present almost the same like what we have on the device characteristic as well. So the voltage wise, in terms of how much your voltage of your device can withstand can be represented as how much RPM you can push on. You can push from 0 to 7,000 or 8,000 RPM, but not all the time you are pushing to that limit. Same goes to the current, and when you push higher voltage in, the higher current will flow into your device or throughout your device. But this is the maximum current that the datasheet is showing. Let's say it shows you it can go up to 50 ampere, but not all the time you're going to use 50 ampere on your apps or application. So you have to justify in terms of selection based on your application. How much current, how much voltage you want to apply to, so you are able to select is it you're going to use a higher end device or just a cheap and sufficient device to cater your application. But both of that limitation in terms of voltage and current is going to be limited by another factor, which is your thermal. And so this is the main point or key point that we're going to highlight to you all regarding your selection. So we have on the panometer that showing you the thermal of your engine. So you can push up to any kind of range in order to fulfill your application requirement, your converter requirement, provided that your temperature gauge is not hitting your red line. You see here, from cool to high. Once it hit red line, maybe something happened to your design, so you have to slow down or you have to decrease your speed, you have to decrease your RPM, maybe at that time you have to stop your operation. So this is what you have to take care. It is the same like in your car. Once your temperature gauge hit certain limit, so you have to stop and take a look at your car or your design. So this is what we're going to see in our thermal application or thermal consideration inside your power electronic design. It means that that's not supposed to be that you have to over design, and because what happens is that when you over design, this is what's going to happen. You put a more cost to your company and it's end up like this. Your boss is going to fire you and the company will be closed. But if it is too low in terms of design spec, so this is what's going to happen. You will have a field recall, which your product will fail at your field, and you have to repair your product, and the cost will jump up like this. So you have a loss inside your company as well. So next, after your first page, there will be a second page showing you all the other datasheet information. And the first thing that important for your device or power switch selection is regarding your safe operating area. Safe operating area means that even though your device is showing that it can operate up to certain voltage and certain current, but within certain condition, you have to reduce or degrade your expectation of the switch, maybe down to certain percent of limitation due to certain kind of environment or scenario. So each power switch device has modified limits, means that you have to reduce or degrade the limits during your operation when the operating frequency is not per what you're supposed to operate or not for what you expected from your design. So it shows here in certain frequency range, your voltage and your current range has to be reduced accordingly. Okay, if you take a look on your certain datasheet, you will see the limitation separately.